Hey everyone, Dr. J here, and in this video we're going to talk about Newtonian gravitational potential. And we're going to start with what is probably one of the most fundamental laws that you learn probably in high school or for sure in a college physics class, and that is Newton's law of universal gravitation. So force, gravity force, I'll use a subscript G for the gravity force. So gravity force is equal to, we have the gravitational constant, times mass number 1 times mass number 2 divided by the distance between the two masses squared. So here, this is our gravitational force, gravity force from Isaac Newton. Really remarkable equation, really a foundational equation for modern or classical physics, I should say. And we're going to start with this equation when we're talking about Newtonian potential. Now, just a couple of things really quickly. This is the universal gravitational constant. That constant, let me write it down here, gravitational constant. Okay, so gravity constant, couple of things about that. One is that I might use different symbols. The book uses gamma. So this is same thing. We're going to use primarily the capital G there, but the book does use gamma, so just keep that in mind when you're looking at those. The other thing is that the units on G can be different depending on whether you're using SI units or CGS units. The CGS unit of acceleration is often called the gal. In SI units, we're talking about meters per second squared. So just be aware if you see different values for the capital G, the gravitational constant, those different values are going to be related to the units in most cases. I'm just going to pull that out here and define it. So R is going to be equal to the square root of x minus x prime, or I'll say x naught. The book uses x prime. I'll say x naught plus y minus y naught squared. Sorry, I overflowed the board here, but this plus z minus z squared, this should also be inside the square root term. So I can maybe kind of, I don't know the best way to write it. This is all what R is. And the reason I want to make this clear is because this is going to come up later when we're doing derivations. We may sort of pull out individual components. So if we're thinking in three-dimensional coordinates, the distance is just we call this the Euclidean distance. This is the x squared plus y squared plus z squared square root of that whole quantity is the distance between 2 points. And in this case, it's the distance between x, y, and z, and the point at the origin. So x naught, y naught, z naught. And if our origin is at 0, 0, 0 in our 3D coordinate system, then of course that would just be, those would drop out, and you would just have x squared plus y squared plus z squared. Square root of that term is distance. So that's our distance term. We've talked about our gravity term. Now let's talk about our mass terms. So we have two masses here. When it comes to the Earth, right, one of these masses is going to be the mass of the Earth. We'll use a capital M for the mass of the Earth. You know, sometimes we'll be using and thinking about the mass in that sense, and that's probably what you may have done in a college class or a high school class. But in this class, we're not going to necessarily think about the mass of the Earth as a constant, right? The mass is changing in space inside the Earth. And so what we want to do is set up some machinery for us to be able to use some mathematical machinery so that we can think about how density is changing inside the Earth or even inside other bodies or other planetary bodies, what have you. So we want to kind of make this framework that Isaac Newton set up more general, so we can use it for more cases. And so let's start by looking at these two masses and saying one of these two masses is our, let's say, the source of our gravity force, and then the other mass is the mass that the force is acting on. And by the way, just as you're looking at this equation, F equals G times M1 times M2 divided by R squared, this has the same form as another equation that Isaac Newton worked on, which is, sorry, I'm getting a little close to the edge here, but this is mass times acceleration. Mass times acceleration is also equal to a force. And you can see here, if you just look back and forth, here's mass 1, the acceleration, and I'll pull that acceleration term out and I'll just put that down here. The gravity acceleration, or actually we often use the term small g. So I'll use small g for gravity acceleration. That is going to equal everything else in this term here. Also remember, sometimes we have a negative sign here, sometimes we have a negative sign here, sometimes we do not. So it just depends on the convention. I think the book is using the negative sign on the potential. So I can throw a negative sign in there. This is equation 3.1 in your textbook. So little g is our gravity acceleration. It's an acceleration, and that's just everything which is left in here. Negative g times m2 over r squared. And again, the negative sign, I guess I should put the negative sign here if I'm going to put it down here. Again, the negative sign is a convention, and it depends on which direction that you're pointing. So if we just imagine drawing two masses, and we've got mass 2 and mass 1, right? We can draw the arrow in this direction, or we can draw the arrow in that direction, and that's where that negative sign comes into play. So don't worry too much about the negative sign. It's mostly just a convention, but you do want to kind of keep track of it if you're doing derivations. So here's our gravity acceleration coming from our gravity force. And a couple things to notice, right? This acceleration is got just one mass in it. So if we're talking about the Earth, right, it would be the mass of the Earth. We still have our gravitational constant, and we still have our distance squared term in there. But now I'm missing something from equation 3.1, and that is the direction here. So this now is actually equation 3.1. And this is just this direction term. So actually, depending on how we define these arrows, we may or may not need the minus sign here, but this r hat, that's our unit vector pointing from the mass m to the observation point p. So I'm using m2 here for the mass of the Earth. So let's just put the mass of the Earth. And then here's some other point. We could call that an observation point. We could call that another test mass. So m1 in this case, right? So we've kept m1. That's our test mass. We call it test mass in college physics usually. It could just be an observation point. Here there's no additional mass, so it's just a location, right? So then by convention, our r hat is going to be pointed from the source to the observation point or test mass or whatever, right? So that's going to be our r hat. And then the gravity force of the mass of the Earth on the mass of the test particle or at the observation point, right? The gravity is going to be going in that direction. It's going to be pulling it in. And so that's why you have this negative sign here now. So with the arrow, r hat defined this way from the source to the test point, then we need this negative sign in there. And again, so I'm going to erase this one because here I haven't added in the unit vector to say direction. So if I was going to add in that unit vector, r hat, I would need to go ahead and put that minus sign in there. So again, a little bit of a convention there, and this is because in college physics, we don't always keep the vector, the unit vector to indicate the direction, but both the force and the acceleration, so now I need to denote this as a vector, these are vectors. And we often just think about the scalar quantity, but if we make these a vector, then we need that r hat and we need that minus sign. Okay, so that's the convention that we'll use in this book. Few things to say about gravity acceleration. This is the gravity field. So gravity field, we call the gravity acceleration the gravity field. Why do we call it that? Well, because it has the properties that the gravity field is the gradient of the gravity potential. This is an important result. The gravity field is the gradient of the gravity potential. You can see here, this looks like a gradient of mass 2 over r. So if we took the potential as, well, we can just directly write it down here. So potential, U, gravity potential meaning the potential due to a gravity force. That's going to just simply equal G times M divided by R. Okay, and notice I'm missing the vector notation, and I'm missing the little unit vector here to say direction. Why is that? because if you'll recall from the previous videos, our potential is not a vector field, it's a scalar field. So the gravity potential is a scalar field. It is scalar valued at every point in space, right? So we have a value for the gravity potential at every point in 3D space. We take the derivative of this, or the negative gradient. Again, sometimes you use negative, sometimes you don't. We take the gradient of this, we get this here. In this case, we should have negative gradient. So the gravity acceleration is the negative gradient of the potential. And here we now have our r hat term, because this is now, and I should add this here, right? So gravity acceleration is a vector quantity. Acceleration in general is a vector quantity, right? So our gravity field is as well. Okay, so a few things about the gravity field as the gradient of the potential. Del cross G is equal to 0. That means the field is irrotational. Irrotational. We talked about this, right, in a previous video, irrotational fields. The gravity field is one of those fields that's irrotational. Okay, so here now we've set up the infrastructure that we need. We started with Newton's law of the gravity force. We noted that we can write this in this way, and we can write this as an acceleration term, right? This is an acceleration. It has the exact form of an acceleration. So the force is equal to some mass times acceleration. The force, the gravity force is here. That means our gravity acceleration is here. We can think about this as, m2 being equal to the Earth, and then that gives us the gravity field of the Earth. If it's just a general mass 2 that we're talking about, then G would not necessarily be the gravity field of the Earth. It would just be the gravity field of whatever that particular object is, a moon or an asteroid or whatever. We noted that this is a field. It's a vector field. And as a vector field, we can write it as the gradient of some potential field. So this now is the gravity potential. And the gravity potential, just by the relationship here between potentials and fields, we can write in this way. Gravity potential, gravity constant times a mass. Again, we can think about this as the mass of the Earth or some other mass divided by distance, where distance is given by this Euclidean distance term here. Okay, so hopefully what you can see now is that gravity is a force. We have to be a little bit careful because gravity is a force. It's a field or an acceleration, and it's a potential. So we have all three of these things that are kind of related to each other, and we have to be careful about which one we're talking about. So in the next section, we'll talk about gravity fields and potentials of various kinds of density distributions. We'll talk about it for the Earth. We'll talk about it for some other shapes as well. And I'll see you in the next video.